EC&M Asks is a video series that enlists the technical expertise of our brand's subject matter experts to answer our readers' most pressing electrical questions. Posted twice per month, these quick videos present Q&As on topics related to various installations, applications, and troubleshooting scenarios. When our readers ask, EC&M answers. Here's Ron Widup with Shermco Industries, who is also a member of NEDA's Standards Review Council.
Hello and welcome to this edition of EC&M Asks. This time we got a question from Kevin, and Kevin asked, hey, I operate a commercial facility and my budgets are limited, so what's the best bang for the buck when it comes to electrical testing and maintenance? The first thing you want to do as the maintenance professional at a facility is do infrared or thermographic surveys. And I'll tell you, it's the best bang for the buck because the system's online, it's energized, and you're going to find a ton of problems while doing the infrared surveys, guarantee you. And the second thing I would do, Kevin, I would make sure, if you have it, which you probably do, is that your ground fault protection on your main breaker or your incoming line works properly. So what is a ground fault? Well, it involves the earth, and also sometimes it can involve electrical equipment. And one of the things we do as testing professionals is we try to eliminate ground faults, but when they do occur, and sometimes they do, we want to make sure we get those cleared and off the system as fast as we can. Hey, one of the things I want to do here in the beginning is to just differentiate what we're talking about. We're not talking about GFCIs or ground fault circuit interrupters. That's the receptacles that are going to be in your garage and in your bathroom. We're talking about ground fault protection of equipment. So it's going to operate at higher current levels, and it's there simply to protect us from fires. The National Electrical Code defines ground fault as an unintentional electrically conductive connection between an ungrounded conductor of an electrical circuit and the normally non-current carrying conductors, metal enclosures, metal raceways, metal equipment, or the earth. Further, the National Electric Code has a definition for ground fault protection of equipment. It's a system intended to provide protection of equipment from damaging line-to-ground fault currents by operating to cause a disconnecting means, that's going to be your main breaker or your main switch, to open all ungrounded conductors of the faulted circuit. The ungrounded conductors, that's going to be your phase conductors. This protection is provided at current levels less than those required to protect from a normal overload situation. So you're going to clear a fault quickly when it goes to ground, and when you have an overload, it's going to take a little bit longer and you're going to get more heating. So we want to see that ground fault, we want to protect it right away. And so where in the NEC does it say you have to do that? Well, Article 215.10 talks about ground fault protection of equipment. Each feeder disconnect rated 1,000 amps or more, if it's installed on a solidly grounded Y system, if it's greater than 150 volts to ground, and if it doesn't exceed 1,000 volts phase to phase, so we're talking about low voltage equipment, and it's in accordance with the provisions of Article 230.95. 230.95, we're going to talk about that here in just a minute. And if you operate a healthcare facility, check out Article 517.17 because there's another layer of protection that you got to have relative to ground fault protection. So why is it that you need ground fault protection in the first place? Well, when you have a fault from phase to ground, those fault currents don't always and oftentimes will not exceed the normal overcurrent protection from the feeder itself. And so you're going to be below the trip ranges of circuit breakers and fuses, and you can get a continuous fault that's going to generate a lot of heat. And that's why we want to sense that fault and clear it. It may appear as a temporary overload, and it could persist for several seconds, minutes, or even longer. And it can cause significant damage, heating, fire, and it can really be a bad thing. So what are we going to do to make sure that we meet the requirements for ground fault protection of equipment? One, we're going to establish an effective ground return path. Also, we're going to specify or design the proper ground fault protection system for the application. We want to supply and install it correctly. And we want to completely test and commission the system to make sure that it works as intended and as designed. So the basic function is this. Typically, you would have the utility service entrance coming in, and that's fed from a transformer, and that transformer will be solidly grounded on the Y connection. That Y connection will go down to the main switch or the main circuit breaker, and then from there it's going to go to feed whatever loads are downstream. So if that system is 1,000 amps or greater, you're going to have ground fault protection on it to clear any faults that could occur. So typically what you're going to have are current transformers to sense the fault. Those current transformers are going to feed a relay which is going to take the fault currents and do something with it. That something is they're going to trip a shunt trip either to open the switch or the circuit breaker. So now we have a ground fault system. We want to energize the building, but who says we have to performance test? Well, these guys right here do. The National Electric Code has an article, 23095C, that is performance testing of ground fault systems. And here's the deal. If you're an electrical inspector and you're not asking for the test record on initial energization of a building that says the ground fault system has been tested, then you could have real liability there. So 23095C says this: the ground fault protection system shall be performance tested when first installed on site. This testing shall be conducted by qualified persons using a test process of primary current injection in accordance with the instructions that shall be provided with the equipment. A written record of this testing shall be made and shall be available to the authority having jurisdiction. So how are we going to make sure that we comply with the National Electric Code? Well, first we're going to use the manufacturer's instructions and recommendations. That's going to be first and foremost. They're going to give us that guidance. Second, we're going to refer to NEMA PB 2.2 2014, which is going to give us a lot of the construction elements and performance elements of that ground fault system. And third, and importantly, what we're going to use is the NETA testing standards to do the field verification and testing of that ground fault protection system in the field. So when we verify performance, we're going to make sure the ground path is effective, the design is right, it's been installed properly, the CTs, the current transformers have the right ratio, polarity, and wiring, the ground fault relay, it operates, it's set correctly, and then we're going to make sure that the overcurrent protective device opens even under fault conditions at reduced voltage. That reduced voltage is 55% of control power voltage on AC or 80% of control power voltage on DC. Hey, let me jump in here with some field advice. This happens almost every time. The ground fault protection system typically ships at the minimum settings. If you don't do something to make sure that it works properly, it's set properly, and that the polarities are right, you can have a lot of problems. We see it almost every time, some issue with the ground fault system after it's been installed. And so how do we test this in the field? We use the NETA testing standards. If you go to section 7.14, it tells you exactly what you need for that ground fault protection system. It tells you the visual mechanical inspections, it tells you the electrical test, and then gives you the expected results. So NETA gives you a very comprehensive set of tests and inspections that you can follow pretty simply through the standard. Let me point out a couple of important ones. One of the things we're checking is the insulation resistance of the control wiring. We want to make sure that that's intact and in good shape. We also want to make sure that it tests by primary current injection. We are going to simulate in a de-energized state fault current through that current transformer, throughout the whole control system, down to the relay, down to the shunt trip, and make sure that the device opens. We're going to do that at the reduced voltage like NEMA tells us to do, and we're going to make sure it all works as intended, as designed, and we're going to do that in the field. Again, simple test, easy to do. I've said several times that we're going to do this by primary current injection, and oftentimes I say, well, it's not possible to do primary current injection at an installation, and that's actually not true. We were involved quite a bit in getting the language of the National Electric Code to say by primary current injection because it's a simple test to do in the field. We've got many years of experience doing this, and all you need is a 110 volt source, an amp bucket, a current supply, and then you can run conductors through the CTs, you can do current injection at the primary current fault level, and then trip the relays. So if you're an inspector out there and somebody says we can't do it by primary current injection, well, that's a misnomer. It's really not true. It's an easy thing to do, so just push back on them. So why does all of this benefit the electrical community? Well, it benefits the manufacturers because it reduces liability from construction damage and installation issues. It benefits the installers because it validates your installation and site conditions, and it reduces liability from improper performance. Hey, if you're an inspector or an authority having jurisdiction, it assures proper installation and compliance with Article 230.95. And if you're an owner, it provides you assurance that your system will operate as intended and as designed, and it's really going to reduce the chance of an electrical fire. So Kevin, I mentioned in the beginning, what's the 2 most important things you can do? Do an infrared survey every year, because you know what that does? It protects you from fires. The other thing I said was make sure you test your ground fault protection system, because you know what that does? It protects you from fires. Those are 2 very simple and very important things when it comes to electrical maintenance. Well, that's it for this edition of EC&M Asks. Hey, if you like these, let us know, and if you don't, let somebody else know. But if you have any questions or want to have a topic you want to talk about, let us know that too. We'd be glad to talk about it.